Namaste, Vanakkam, and welcome back to MidhaGuru. It's me, Manan, the math faculty. Well, have you ever stumbled across problems such as how many bricks we require to make a wall of certain height, length and breadth, or the amount of paint required to paint the 4 walls of a room except the ceiling and the floor? Well, this comes under a very broad topic in mathematics known as mensuration, and particularly the surface area and volume of solids. And in today's lesson, we are going to cover all the types of solids like a cube, a cuboid or a cylinder, a cone, a sphere, and also the conversion and combination of these various solids. Well, without further ado, let's get into the lesson. So before we get into the lesson, let us see what our aim to learn here is. The first is to understand how to calculate the surface area and the volume of different types of solids. The second is to understand how two solids can be combined together to form a complex solid and how we are supposed to calculate the volume and the surface area of such complex solids. The third is the idea of conversion, what conversion is and how it applies to our topic today. And the last is to apply this knowledge in our day-to-day lives as well as our problems with studies. So let's get into the lesson. But before we begin, do you know what this word volume means? Many people also refer to it as capacity. But well, what does even capacity mean? If you do not know this, then the most simple way to understand this is if you have a vessel of certain dimensions, its capacity of volume is the amount of water or air that you can store inside it. But how did we arrive at volume? For that, we need to go back to the most basic unit of measurement. If we have a single dimensional object, such as a straight line, we had a single dimensional quantity to measure it, that is known as length. And to express this length, we had single dimensional units such as meters, centimeters, inches, feet, and so on. When I translated the single dimensional object in the other dimension, that is extended it in the other axis, I got what we call plane figures or 2D figures. To measure this 2D figure, we had a 2D quantity known as area. And to express this area, we had 2D units such as centimeter squares, meter squares, inches squares, and so on and so forth. And when I translate this 2D object into the third dimension, I get what we call or refer to as solids. Now this figure has 3 dimensions, namely it has a length, a breadth, and the third dimension, that is its height. So to measure such a 3D object, we needed a 3D quantity, and we named it as the volume. And to express this volume, we also needed 3D units, and we made units such as centimeter cubed, meter cubed, inches cubed, and so on. So let's move on. After volume, we have another type of quantity for these solid figures, that is known as surface area. But do not confuse surface area with area of 2D figures. So let us try to understand what surface area is. Well, let us say I have a figure that we call as a cube. The most easy way to understand surface area is, let's say this is a gift box and I need to cover it with wrapping paper. So the area of the wrapping paper that is needed to exactly cover this box is the surface area of this particular box. In the same way, all 3D solids have some surface area or the area of all the outer surfaces added up. That is what we call as surface area. So now let's move on into the solids one by one and see what their applications are. The first solid, as you can see on the board, is a cube. But what is a cube? Well, a cube is a 3-dimensional object in which the length, breadth and height are all of same measurement. That is, let's say they are all of a length. So this cube no matter from where you see it, all the edges and all the faces are of equal measurements. Well, what will be the volume of this cube? So, let us go back to our understanding of volume. As I told you, when I translated a 2D figure into the third dimension, I got volume. And the 2D figure itself arrived from the translation of a single dimensional object into the second dimension. So if this square had sides A, and the length of the line was A itself, and we extended it for A units, that is how we arrived at the area formula, that is A into A. And in the same way, when we translated this 2D square into the third dimension to arrive at a cube, the volume can be calculated by calculating the area of the cross section into the length that it has been extended. In this case, the area of the cross section is nothing but the area of the square, so we write that down as A into A. And the length we extend it, as you can see, is also A. So we arrive at the formula that the volume of a cube is equal to A cubed, where A is the side of the cube. Now, a cube has two types of surface areas. One we call as the total surface area, that is the area of all the surfaces, and the other is known as the lateral surface area. What is lateral surface area, you may ask? We'll get into that in a moment. First, the total surface area is the sum of the area of all the surfaces of the particular solid, in this case the cube. Well, to understand this, let us see what happens if we open up a cube. If you visualize this, when we open up a cube, we get something that looks like this. As you can see, it has 6 faces, and when we fold it up back together, we'll get a cube. Well, as we know, all the sides of the particular faces are all of length A. This means that we have 6 squares with sides A. The area of any one of these faces can be given by the square area formula, that is A into A, which means A squared. And as we have 6 such faces, we can give that the total surface area is equal to 6 into the area of one face, that is A squared. So we get 6A squared. This is the total surface area of said cube. Well, what is lateral surface area? For this, you need to imagine a bit. Just imagine that you are sitting in a room that is cubical in shape, that is, its length, breadth and height are all of same measurement. The lateral surface area would be the area of the faces that you can see right in front of you without tilting your head upwards or downwards. That means, excluding the ceiling and the floor, the walls of the room form the lateral surface area. With respect to the cube, that would mean the area of all the 4 sides that are standing upright. And we exclude the ceiling and the floor. As we already calculated, the area of any one of these faces is A square on a cube, and as you can see, we are calculating the area of 4 faces and excluding 2. We get that lateral surface area of a cube would be equal to 4A squared, as it is the area of 4 faces. You may or may not have understood what we learned so far, but if we applied this to a few example problems, we may get a better understanding. A very interesting problem that I came across once was that a metal sheet is used to make a water tanker in the shape of a cube with length of edge 12 meters. The question asked to explain how much volume of water could be stored in this particular tank and how much metal sheet was required to make this tank. Let us understand this better. So if we draw this particular cube, we get something like this, and as we know, the length of the edge is 12 meters. So now, the first part of the question states what the volume of said cube is. As we learned, the volume of a cube is nothing but A cubed, where A would be the length of the edge. So we directly calculate that as volume of this cube is equal to 12 cubed. If we do this calculation, we would get it would be 1728 meter cubes of water. Before we move ahead, a very important thing that I would like to tell all of you students is that in this particular topic, that is mensuration, calculation of anything, the units are of utmost importance. If you write meter or meter square here, your answer is as good as wrong. So please avoid making such mistakes. Moving on, so now we have calculated the amount of water that can be stored inside this cube. The second part of the question required us to calculate how much metal sheet would be required to make said tanker. Here, there's a bit of understanding required. If it asked how much paint we had to apply on its walls, you know that the ceiling and the bottom is never painted. So we would have to calculate the lateral surface area. But here, it asks us metal sheet, which is present on all sides. So we need to calculate the total surface area. Well, total surface area of a cube can be given by the formula 6 into a squared, right? Applying this to our cube right here, we get 6 into 12 squared, which would be equal to 6 into 144. Again, calculating this, we get 864 meters squared. Why is the unit here meters squared? Very good, because this is a quantity of 2 dimensions. Let's move on to the next solid. The next solid, as you can see, is in this lovely shape. It is known as a cuboid, or is in some places referred to as a rectangular solid. And it is exactly what the name suggests. It is a translation of a rectangle in the third dimension. Let us see how it's formed. See, we have a rectangle that's a 2D object, and when we translate this into the third dimension, a cuboid is what I get. If you are not able to visualize this in your mind, think of a matchbox, your lunch box, or your mathematics book. If you look at it from all sides, this is exactly what it would look like. This is what we call a cuboid. The difference between a cube and a cuboid is much similar to the difference between a rectangle and a square. Just as in a square the two sides were equal and in a rectangle both were different, in a cuboid all three are of different measurements. In some special cases, the cuboid might have two lengths of the same measurement, but the third must be different. That is, length could be equal to breadth but must not be equal to h, or they all three are not equal to each other. That is how a cuboid is formed. Let us name these sides as L, B and H. So, moving back to our fundamentals. I said that to calculate the volume, you need to know the area of the cross section and multiply it by the length it was extended to. Let us consider this rectangle on the floor as our cross section. We can clearly see that its area is length into breadth. And to calculate the volume, we must multiply it by the length that it was extended. And as you can clearly see, the length that here it is extended to is h, or the height of the cuboid. So we multiply this by h, and this is how we arrive at the formula that the volume of a cuboid can be given by L into B into h. This particular solid also has a total surface area and a lateral surface area quite similar to the cube. Well, what would be the total surface area? As we understood in the cube, the total surface area would be the area of all the faces combined. If you look at this cuboid, the bottom is a rectangle of L into B. Well, what about the rectangle on the top? Yes, it's the same. It is also length times breadth. In the same way, you can see this rectangle here is breadth times height, and this rectangle here is length times height, and they have the exact copies on the opposite edges. This would mean that we have 6 faces that are in pairs of 2. One is length into breadth, one pair is breadth into height, and the third pair is length into height. So if we just take the 2 out common, we get L into B plus B into H plus H into L. This is the formula to calculate the total surface area of a cuboid. Now what would the lateral surface area of said cuboid be? As I said, imagine you are sitting in a cuboidal room. Well, that is the shape of most rooms. Don't consider the ceiling and the floor. The 4 walls that you see in front of you would constitute the lateral area of said cuboid. In this case, you can clearly see 2 faces are length into height and 2 faces are breadth times height. So if we write that down, we get L into H plus B into H. And if we take out the H's common, we get that the lateral surface area of a cuboid would be twice its height into the sum of the length and the breadth. Well, let us move on and try to understand what kind of problems we'll deal with when we talk about cuboids. Another interesting example problem that I came across related to cuboids was that a conference hall was built with the dimensions 12 into 9 into 5 all in meters. The first mistake that many children make is they get confused with what should be the length, breadth and height. It is in that particular order the dimensions of cuboids are always written. The order being related to the volume of the cuboid. We write the volume as L times B times H, right? This would be the length, this would be the breadth and this would be the height. And I ask you to always stick to that particular method to avoid any confusion. Coming to a question, if I draw the conference hall that we are discussing about, it would look something like this, right? The question required us to calculate the amount of air present in said hall and the cost of painting the 4 walls at ₹10 per meter square. Well, the first part of the question requires us to calculate the volume of air present in this particular hall. And going back to what I earlier said, if this is our vessel, the volume of air present inside it would represent the volume of said vessel. Well, for that we need to calculate the volume of this cuboidal room. And we know that volume of cuboids can be given by the formula length times breadth times height. So on calculation, we get 12 into 9 into 5, which can be given 108 into 5 would be 540 meter cubes of air. This is the amount of air present in said conference hall. The second part says the cost of painting at the rate of ₹10 per meter square, but it only mentioned that we are supposed to paint the 4 walls of the room, not the ceiling, not the floor. What are we supposed to calculate here? Put your thinking hats on. Very good. We are supposed to calculate the lateral surface area of this particular cuboid. Well, by formula, the lateral surface area of a cuboid can be given by the formula 2H L plus B. So if we just substitute these values, we get 2 into 5, 12 plus 9. 2 into 5 would be 10 and 12 plus 9 is 21. So we get 210 meters square. This is the area that is required to be painted. The problem doesn't end here. We are supposed to calculate the cost at the rate of ₹10 per meter square. And we know that cost can be given by rate multiplied by the area. So 10 into 210 would be equal to 2100 rupees. This is the amount of money required to paint the 4 walls of said room. Moving on to the next solid. The next solid may look very similar to many things you see around your house. Your water bottle, your kitchen tumbler, and the bottles that your mummy keeps masala in. This is what we call a cylinder. How did we get a cylinder, you ask? Well, if I had a circle that we all know is a 2D object, its area can be given by pi r square, right? Now when I translated this 2D circle in the third dimension, I got a figure that looks much like this, and as you can see, this and this are quite similar, right? So this is what we call a cylinder. The all important question, how do we calculate the volume of a cylinder? Going back to our basics, the volume would be the area of the cross section by the length that it was extended to. In this case, let us say we extended it to the length h. The area of the cross section being pi r square, we get that the volume of a cylinder can be given by the formula pi r square times h. Again, we have two types of area in this particular solid. One is known as the total surface area, as you all know, the area of all the surfaces. The second is quite similar to lateral surface area, but it is called the curved surface area, that is the surface area of all the curved faces. As you can clearly see, it has a circular face here and here, and they are both flat, right? The curved surface area is the area of this entire curved region. As you can see, this part of the cylinder, excluding the flat faces at the bottom and the top. So, total surface area can be given by the area of these two circular faces and the curved surface area. So it would serve us well to calculate the curved surface area first. Let's imagine that I cut this cylinder across a straight line here and open out its surface. What would it look like? It would look something like this, right? It has two circular faces, and when I slit this curved surface open, it would open out like a rectangle, right? What would be the length of this rectangle? The breadth is clearly the length of the cylinder, that is height. But what would be the length of said rectangle? If you could go back, we slit it from this cylinder, right? So when I put it back together, the length would be somewhat equal to that, right? What is that called? Very good, it's called the circumference of the circular face, which we all know can be given by 2 pi r. Now this circular face has an area of pi r square, so does this. What is the area of said rectangle? Yes, it would be 2 pi r times h. So the curved surface area is clearly the area of this rectangle, so we write that down as 2 pi r h. And please do well to remember these formulas. So now the total surface area is the area of this curved surface and the area of the two circular faces, which can be given by 2 pi r h, which is the curved surface area, plus 2 pi r square, as there are two circular faces. If we can take 2 pi r out common, we get 2 pi r into h plus r. This formula gives us the total surface area of a solid cylinder. The next type of solid is also a cylinder, but it is a special type of cylinder that we call hollow. As you can clearly see, this cylinder has some thickness, but it is hollow through the center, unlike the cylinder that we saw before. So we call this as a hollow cylinder. Where have you seen hollow cylinders? If you have water pipes, electrical pipes, or pipes of any sort at your house, just take a look at them. They look quite like this, right? The thickness of the cylinder may vary in different cases, but they look quite similar to this. They have a hollow channel through that can allow air and water to pass. Well, in this case, now the top and bottom circular faces would look something like this. To calculate the volume it would be better to understand it in this way, that we had a huge cylinder and we removed a smaller cylinder away from it. Let's just name this outer radius as capital R and this inner radius as small r. So to understand better, we had a cylinder of radius capital R and we removed a cylinder of radius small r from inside it. We were left with this particular hollow cylinder. Let us say the height of this cylinder is h. We already know the volume of a cylinder can be given by pi r square h. But it's not so simple here. It is a bigger cylinder and a smaller cylinder has been removed from it. Apply that same very logic to the volume. So the volume of said hollow cylinder is the volume of the larger cylinder, which has a radius capital R, which would mean pi r square h, and a smaller cylinder of radius small r removed from it, which means we are supposed to subtract the volume of the smaller cylinder. We arrive to this formula. Taking pi and h common, we get that the volume of a hollow cylinder is equal to pi h times r square minus small r square. Capital R being the radius of the outer face and the small r being the radius of the inner circular face. So now, what would be the total surface area? As in the case of cylinder, it would serve us well if we could first calculate the area of this curved surface. To understand here, you need to understand a very simple logic that in a solid cylinder, there's only one curved surface. But as you can clearly see, this cylinder has two curved surfaces. One is the surface on the outside and one is the surface on the inside. So let us see. Quite opposed to what we wrote as the volume, here we can calculate this by writing 2 pi rh and adding, as I said there are two surfaces, each separate, we need to add 2 pi times small rh. Taking 2 pi h as common, we get 2 pi h r plus r. This formula gives us the curved surface area of said hollow cylinder. Now have a careful look at these circular faces. The area of this larger circle with radius r would be pi r square, right? And the radius of the smaller circle with radius small r would be small pi r square. This would give us the area of said particular circular face. And as we have two, we can give the area of these two circular faces as 2 pi into r square minus r square. Okay? Now the total surface area is the area of these two circular faces and combined with the curved surface area, which we can give as 2 pi r square minus r square plus 2 pi h into r plus r. This formula gives us the total surface area of a hollow cylinder. The next solid is one you kids like a lot. It's called a right circular cone. It may not look similar from here, but if you put it upside down, it's what your favorite ice cream cone looks like. Well, how did we arrive at a cone? If I have a right triangle and I rotate it about this axis, it would make a shape something like this, right? And if you look at it from the bottom, it would look circular. That is exactly what a right circular cone is. Said right circular cone has a circular face, which would mean that it would have some sort of radius. We name this radius as smaller, and this perpendicular height to the radius we call as h. In a cone, there is another height that we call as the slant height, that is the height of this triangular face. We can write that down as L. Before we go into anything further, as you can see, this is a right triangle, so L, and this would be the radius, right? So L square is equal to h square plus r square. This is a very important relationship and it would do us quite good if we can remember this. Moving on. The volume of said right circular cone, I cannot derive it for you, but I can explain this to you that if you can't remember it, remember that a circular cone of any radius or height has the volume equal to 1/3 of a cylinder of the same radius and height. The volume of the cylinder can be given by pi r square h, and as I said, 1/3. This formula gives us the volume for a right circular cone. Now again, if you can look at it carefully, just look at it for a second. It has two types of area. One is the area of this flat circular face down here. The other is the area of this triangular circular part, right? This is known as the curved surface area, and this would be the flat surface area, and together they form the total surface area. Just as in the case of cylinders, let us first calculate the curved surface area. This is given by the formula pi times r times L. L being nothing but the slant height of said right circular cone. So now what is the total surface area of said cone? The circular flat face at the bottom has a radius r, so its area should be pi r square, right? So now the total surface area is the curved surface area plus the area of the circular face. If we take pi r as common, we get the formula for total surface area as pi times r into L plus r. The most common types of problems that we get from this particular topic are related to tents and how much canvas is required to make said tent. Let us look at this problem in a bit of depth. Coming to this problem, let us say the question says that we are supposed to form a tent that has a radius of 6 meters, a height of 8 meters, and we are supposed to calculate the area of canvas cloth required to make said tent. How do we go about this? Well, if you imagine this in your brain, the area of canvas required would be the curved surface area of said right circular cone. Why, you ask? Because have you ever seen a tent with a floor in it? No, right? So, to calculate the curved surface area, we just need to apply the formula pi times r times L. But hold on, there's something missing, right? If you can clearly see, we don't have the slant height L. But again, by Pythagoras theorem, the relation stands that this L squared would be equal to 6 squared plus 8 squared, which gives us 36 plus 64 or 100. So L square is equal to 100, so L would therefore be equal to 10 meters. It should have been plus minus, but as in measurement we cannot have any negative quantities, right? So L, or the slant height, is equal to 10 meters. Now we can go about calculating the curved surface area, which would be equal to 22 by 7 into the radius, that is 6 into 8, or we write down as 3.14 into 48. Calculating this, we would get area roughly equal to 150.72 meters squared. This would be the area of the canvas cloth required to create said tent. Let's move on to the next type of solid. Do you guys recognize this from somewhere? Well, it is the most favorite playing toy all around the world. Many kids like cricket balls, many like footballs, many like basketballs, some even like golf balls. Well, do you know what the shape of a ball is called? It is called a sphere. How did it get to a sphere, you may ask? So if a circle is rotated around any one of its diameters, a sphere is what we get. Well, a sphere has a radius in this direction, a radius in this direction, and a radius in the third dimension as well. If you can imagine this arrow coming out of the screen. So, all important question, what is the volume of a sphere. It is given by the formula 4 by 3 pi times r cubed. To explain this formula, it would take some calculus and a lot of mathematics, but we will not get into it today. So, now you may ask me, what kind of areas does this sphere have? In the most layman way, if you can just look at it, you can clearly see there are no flat surfaces. There is only one curved surface all around the sphere. So the curved surface area and total surface area for this particular solid are one and the same. So we just write that down as the total surface area. And to remember the total surface area, a very wonderful explanation that I once read was that it is just equal to the area of the shadow formed by this sphere on the ground times 4. That is pi r square into 4, or we can write down that as 4 pi r square. This would give us the total surface area of this particular sphere. The next type of solid is quite related to a sphere. In fact, it is a sphere cut into two equal halves. Each half is known as a hemisphere. So this hemisphere is half of a sphere of radius r. That is, this sphere was cut into two equal parts and we arrived at a hemisphere. Now the difference that you can be able to see on the screen very clearly is that if the sphere had only one curved surface all around, this does not have so. It has a curved surface area and a flat circular face as well. The area of the flat circular face we can easily calculate as pi r square. But what is the curved surface area of this hemisphere? Well, if you imagine the whole sphere, the curved surface area was 4 pi r square, and this is half of it. So the curved surface area must be equal to half of that, which would be 2 pi r squared, right? And so the total surface area should be this curved surface area plus the area of this circular face, which would give us 2 pi r squared plus pi r squared, or 3 pi r squared. Coming to the volume of this hemisphere, so its volume will be equal to half of the original sphere that was cut into two pieces, which means the volume will be equal to 2 by 3 pi times r cubed. This formula would give us the volume of said hemisphere. Now that we have covered all the simple solids, let us move on to the topic called combination. But what is combination? Well, as you can see, this shape looks quite like a capsule, medicine you take when you are ill, and this looks like one of those kryptonite crystals that was used in the Superman movie. But you may say that, sir, you never taught such solids to us. We never saw a solid of this shape in the lesson that you taught so far. Well, how do we calculate the measurements of said solids? Well, it's very simple. It may look very tough, but it is in fact very simple. If you cut this capsule from here and here, you get two hemispheres and a cylinder in the middle. And in the same way, if you cut this across this line and this line, you get a cuboid and two pyramids. And that is exactly what combination is. We use two or more simple solids to make a more complex solid. For example, we make a rocket by joining a cylinder with a cone at its top. Your gulab jamun comes in more forms than one. Have you seen a gulab jamun that looks quite like this? Well, this is formed by adding two hemispheres on both ends to a cylinder. There can be many permutations and combinations to form solids from two or more different solids. If I combine a hemisphere with a cone, it looks like this. If I combine a cone on top of a cube, it would look a bit odd, but this is something almost what it would look like. So there can be many combinations formed from solids by joining two or more of them together. How do we calculate the area and the volume, you may ask? Well, the step that we just used to make these particular solids, we move back. Here I had a cone and a cylinder. As you can see, the radius of this cylinder and the cone is quite the same, and we will have some height for the cylinder and some height for the cone as well. So we calculate the volume of this cone separately, and we calculate the volume of the cylinder separately. Then we add both of them to get the total volume of said combination of solids. The same applies to all combinations, not only here on the board, out in the world and in your maths book as well. The next topic that we are going to see is conversion. But before we begin, what does conversion mean? It means transforming one object into different objects, or transforming one object into the same object but of different sizes. For example, we have a huge metallic sphere here, and when we melt it and recast it into 6 different spheres but of smaller radius. As you can see, this is a huge sphere, but these are quite smaller than that big sphere. Or to form different shapes, here we have a cylinder of some arbitrary radius and height, but we melt it down to form 4 cones which are of different heights and radii. This is what conversion means. But what does it mean for us mathematically? There are many problems related to conversion, but the most interesting one that I saw, and that would pass under your radar as you would not be able to think that it's a problem of conversion, was that there is some ice cream stored in a cylindrical tub, and it is supposed to be separated to a said number of children in ice cream cones. And we were supposed to calculate the volume of ice cream that each kid gets. How do we do this, you may ask? So let us say this has a volume of, let's say, 10,000 centimeters cubes. So we have 10,000 centimeter cube of ice cream, and it is said that we are supposed to distribute this to 100 children in cones. This means that each cone would have 100 of this, or 100 centimeter cubes of ice cream in them. Now let's say the radius of this cone is given as 10 centimeters. We are supposed to calculate the height. We know that the volume of a cone is given by the formula 1 by 3 pi times r square h. We know the r, and we know the total volume of this cone is 100. So we write down 100 is equal to 1 by 3 into 3.14 into 100 into the height. We cancel out 100 on both sides, excuse me, and we get roughly equal to 1.04. So we write this down as 1.04 times h is equal to 1, or h is equal to 1 over 1.04 centimeters. As all the values are taken at random, this is a fraction, but this is how conversion is applied in the real world. Now, as you have come to the end of whatever we had to learn, let us solve a few example problems together to get it more inside your head, everything that we studied today. The first example problem says that a solid iron pole consists of a cylinder of height 210 centimeters and base diameter 24, which is surmounted by another cylinder of height 60 and radius 7 centimeters. Before we move ahead and see what the question is asking, let us draw a rough diagram. The first part says that there is a cylinder of base diameter 24, which would mean that the base radius would be 12 centimeters, and it has a height of 210. This has been surmounted by another cylinder that has a height of 60 centimeters and a radius of 7 centimeters. Now, we are supposed to calculate the mass of the pole, given that the density of iron is 8 gram per centimeter cube. That is, every centimeter cube of iron weighs 8 grams. So let us calculate the volume of this particular combination of two cylinders. How we do that? Well, we separate it into two different cylinders, or as you can see, it is clearly two different. So let us see. The volume of this particular cylinder would be given as pi r squared h. Here the radius is 7 and the height is 60. Substituting that, we get 22 by 7 into 7 times 7 into 60. If we cancel this out, we get this is the volume of the thinner, smaller cylinder on the top. Now the volume of this larger cylinder is also given by the formula pi r squared h, but here the radius and height are different. So we write down 22 by 7 into 12 squared into h. This cancels out at 30. So the rest of the calculation would be this is the volume of the larger cylinder. So now the total volume of this whole cylinder would be equal to the sum of these two, that is 95040 plus 9240, which would give us 104,280 centimeter cubes. But a problem is not over yet. It says that every centimeter cube weighs 8 grams and we are supposed to calculate the mass. So let us multiply this volume by 8. We get this is the weight of this total combination of two cylinders. Or if we convert that into kilograms, we get 834.24 kgs. This would be the weight of this combination. Let us move on to the next example problem. Our next example problem says that a solid is composed of a cylinder with hemispherical ends. If the whole length of the solid is 104 and the radius is 7 centimeters respectively, find the cost of polishing its surface at 50 paise per centimeter squared. Seeing this word surface, it's quite clear that we are supposed to calculate the total surface area of said solid. Before anything, if we draw a rough diagram of this solid, we get something like this. It says that its total length is 104 centimeter and the radius of the hemispherical ends are 7 centimeters, right? So, of the top of your head, if this is 7 and this is 7, what would be the length or the height of said cylindrical part? It would be 104 minus 14, which is 90 centimeters. Now just imagine if I cut this along these two lines, what happens if I join the two hemispheres? Well, they are of equal radius, so they would form a whole sphere, right? So let us calculate the surface areas separately of the sphere and the cylinder. The cylinder also has a radius of 7 centimeters and a height of 90 centimeters. And the sphere has a radius of 7 centimeters. You know how to calculate the total surface area. I say total surface area because in a sphere both are one and the same thing. It is given by 4 pi times r square. So if we write that down, we get this would be equal 616 centimeters squared. Now to calculate the surface area of the cylinder, but before we do that, which surface area are we supposed to calculate? As you can clearly see, we are not supposed to calculate the surface areas of the two circular faces as they are covered by the hemispheres. We are only supposed to calculate the area of this central part, which would be its curved surface area. And we know that the curved surface area of a cylinder can be given by the formula 2 pi r h. So 2 into 22 by 7 into the radius being 7 into 90. When we calculate all this, we get this would be the curved surface area of this central cylindrical part. Now the total surface area of this entire solid is the sum of both of them. So we get that the total surface area is nothing but 3960 plus 616, which would give us 6 plus 6, 7, 6 plus 9, 4576 centimeters squared. But our problem does not end there. We are supposed to calculate the cost of polishing. Well, the cost is always equal to rate into the total surface area. The rate here is 50 paise per centimeter square or half a rupee into 4576, which is our total area. So when we calculate this, we get it would take rupees 2288 to polish this entire solid. The next example problem says that a circle tent has a cylindrical shape surmounted by a conical roof. Before going any deeper, let us just draw a diagram. It looks something like this, right? Now moving ahead, the radius of the cylindrical base is 20 meters. The heights of the cylindrical and conical portions are 4.2 and 2.1 respectively. That is, this height is 4.2 and this height is 2.1, all in meters. Find the volume of air present in the tent. If we just cut it along this line, we can clearly see that there are two solids, one being a cone, the second being a cylinder. Now the radius of this cone is same as the cylinder, that is 20 meters, and its height is 2.1 meters. In case of the cylinder, the radius is same, that is 20 meters, only the height is equal to 4.2 meters. So now applying the formula of volume for both, we get that the volume of a cone is 1 by 3 pi r square times h, or 1 by 3 into 22 by 7 into the radius being 20 into 20 into the height 2.1. This would go into this 0.3 times, or we can cancel out this 0.3 and cancel this 0. This 3 could be cut with 3. Now we get 22 into 40, which is equal so sorry for my mistake, it's 880 meter cubed. This is the volume of the conical part. Let us calculate the volume for this cylindrical part. The volume of this cylinder can be given by pi r square times h, that is 22 by 7 into 20 squared into 4.2. As you know, this can go into this 0.6 times, right? So now on calculating, we will get the volume is equal to 5280 meter cubed. So the total amount of air present in this whole tent would be equal to 5280 plus 880, which gives us so this particular tent has an air equal to 6160 meter cubes. So kids, we have now come to the end of our lesson, but if there's still something that you would like me to explain or something that you did not understand, please leave it in the comments down below. Subscribe to our channel and join the MidhaGuru family today. Thank you.